When light leaves a star that is 1 billion light-years away, it travels for 1 billion years before reaching your eyes. 1 billion years. That is longer than complex life has existed on Earth. And yet, here is the strange thing. From the light's own perspective, if we can even say such a thing, no time passes at all. Not 1 second, not 1 billionth of a second, nothing. Zero. The journey that takes 1 billion years for us takes no time whatsoever for the light itself. How can that be? How can something travel for 1 billion years and yet experience no time at all? To understand this, we first need to talk about time itself. What is time? You might say that time is what clocks measure, and that is a reasonable answer. But what do clocks actually do? A clock is simply a process that repeats regularly. A pendulum swinging back and forth, a quartz crystal vibrating, or an atom changing between energy states. We count those repetitions, and we call that time. This means that time, for any object, is related to the processes happening inside that object. Now imagine that you and I both have perfectly identical clocks. As long as we stand next to each other, our clocks tick at exactly the same rate. 1 second for you, 1 second for me. But now imagine that you climb into a spaceship and begin traveling away from me at an extremely high speed. From your point of view, your clock works perfectly normally. Everything feels exactly the same as always. But from my point of view, watching you move away, your clock begins to run slower. Not because it is broken, not because anything is wrong with it, but because space and time themselves work that way. This effect is called time dilation. It means that the faster you move, the more slowly time passes for you compared to someone who remains at rest. And this is not just theory. This effect has been tested many times using atomic clocks placed on airplanes and satellites. And the results match Einstein's predictions perfectly. Now we arrive at Einstein's key idea. Light always travels at exactly the same speed for every observer, about 300,000 kilometers per second. It doesn't matter whether you are standing still or moving extremely fast. You will always measure the same speed of light. This is very strange because normally velocities add together. If you throw a ball while moving, the speed of the ball changes depending on your motion. But with light, that does not happen. Einstein realized that if the speed of light is always the same, then something else must change. And what changes is time itself. Time is not absolute. There is no universal clock for the entire universe. Every object has its own time, depending on how it moves through space. We can think of space and time as combined into something called space-time. Everything in the universe moves through space-time at the same total speed, the speed of light. If you are not moving through space, then all of your motion is through time. Time passes normally. But if you begin moving through space, part of your motion is used for moving through space. That means less motion remains for moving through time. So time passes more slowly for you. The faster you move, the slower your time flows. And if you could reach the speed of light, all of your motion would be through space. There would be no motion left for time. The result would be that time stops completely. And that is why we say that time does not pass for light. When a photon leaves a distant star and travels for 1 billion years before entering your eye, from its own perspective the entire journey happens instantly. The emission and the absorption occur in the same moment. This is not poetry. This is real physics derived directly from the equations of Einstein's special relativity. Of course, from your own point of view, everything feels completely normal. Your heart beats at its usual rhythm, your thoughts flow as they always have, and your clock ticks with perfect regularity. You do not feel that time has slowed down. You do not feel trapped in some kind of cosmic slow motion. For you, a second is still a second. It always will be. This is one of the most important and most difficult ideas in relativity. No one feels their own time changing. Your own time, what physicists call proper time, always flows normally for you. The difference only appears when we compare your time with that of someone who is moving differently through space-time, and this is where the mind begins to protest. Because naturally we want to ask, all right, but who is actually right, the one who stayed still, or the one who traveled? Einstein's deep answer is this: both are right within their own frame of reference. There is no absolute point of view in the universe from which we can say who is really moving and who is truly at rest. Absolute rest does not exist. Only relative motion exists. This feels strange because it contradicts our everyday intuition. In daily life, it feels as if the world is stationary and we move through it. It feels as if time is a universal river, flowing the same for everyone. But relativity tells us otherwise. Each observer carries their own clock, their own time, their own way of slicing reality into past, present, and future. Now, if that idea already feels unsettling, consider something even stranger. Not only does time depend on motion, space does too. Distances change, sizes change. What one observer measures as a certain length, another observer moving relative to them will measure as a different length. This effect is called length contraction. Imagine an enormous spaceship, very long, traveling close to the speed of light. For the people inside the ship, everything appears completely normal. If they walk from the back of the ship to the front, the distance is exactly what it has always been. But for someone watching the ship race past at incredible speed, the ship appears compressed along the direction of motion, not because some physical force crushed it, but because space itself behaves that way under extreme relative motion. Time runs slower, lengths become shorter, and all of this happens to preserve one single principle, that the speed of light is the same for everyone. This constancy of the speed of light is not just a strange curiosity, it is the key that reshapes our entire understanding of the universe. Now let me show you something even more beautiful. We often talk about space and time as if they were separate things, as if space were the stage, and time were the clock ticking somewhere in the background. But that picture no longer works in relativity. Space and time are woven together into a single four-dimensional structure called space-time. Every event in the universe, a star exploding, a hand rising, a word spoken, a photon emitted, has both a position in space and a moment in time. You cannot fully describe an event by saying where it happened. You must also say when it happened. Space and time are inseparable, and here is the profound part. Different observers do not agree on how to divide space-time into space and time. What is here and now for me may not be exactly here and now for you, if you are moving relative to me. Two observers in motion relative to one another slice space-time differently. That is why they disagree about time intervals and distances. This leads to another famous consequence of relativity, the relativity of simultaneity. Most people believe that if two events happen at the same time, then they happen at the same time for everyone. It seems obvious, but in relativity, that is not true. Two events that are simultaneous for one observer may not be simultaneous for another observer, moving relative to the first. Imagine a very long train. Lightning strikes the front and the back of the train at exactly the same moment, according to a person standing on the platform in the middle. The light from both strikes reaches that person at the same time, so they conclude that the strikes happen simultaneously. But now imagine a person sitting at the center of the train, moving forward with it. That person moves toward the light from the strike at the front, and away from the light from the strike at the back. Because the speed of light is the same in both directions, the light from the front reaches them first. That observer concludes that the lightning at the front happened before the one at the back. So who is correct? Both of them. Not because someone is confused, not because information arrived late, but because simultaneity itself depends on the observer's motion. This radically changes our idea of the present. We like to imagine that there exists a universal now spreading across the entire universe. Relativity tells us that such a universal now does not exist. My distant present and your distant present may not match if we are moving differently. Once you accept this, you begin to see why the idea of time for light becomes so subtle. Even for ordinary objects, time is no longer absolute. It depends on the path an object takes through space-time. This brings us to an important concept, the space-time interval. In ordinary geometry, if you want to find the distance between 2 points, you use the Pythagorean theorem. Move 3 meters one way and 4 meters another, and the straight line distance is 5 meters. Space-time has something like a modified version of this rule. But time enters the equation with a different sign, and that mathematical difference is exactly why moving faster through space means moving less through time. You do not need to memorize the equation to understand the idea. The important point is this: the universe has a geometry different from what our intuition expects. Relativity is not just a collection of strange tricks, it is a new geometry of reality. In that geometry, every object traces a path through space-time called a world line. You have one, I have one, a planet has one, a photon has one. Your world line represents your entire history, where you are at every moment of your life. If you sit still in a room, your world line points mostly in the direction of time. If you run, your line tilts slightly toward space. If you travel in a spacecraft at extreme speed, it tilts even more, and a photon, which always moves at the speed of light, follows a special limiting path through spacetime, one for which the proper time between emission and absorption is zero. That is what we mean, in a precise physical sense, when we say time does not pass for light. But we must be careful. It does not mean that light experiences the entire universe instantly. It does not mean photons have awareness. We should not humanize light. What it means is that within the mathematical structure of spacetime, the proper time along a photon's path is zero. This may sound abstract, but it is actually astonishing. It means that nature allows connections between events, separated by vast distances, without any passage of proper time along the path of light. And if this still feels unreal, consider something tangible: cosmic rays. Subatomic particles constantly strike Earth's atmosphere from space. Some of the particles produced there are called muons. Muons are unstable. At rest, they live only a tiny fraction of a second before decaying. According to classical physics, many of them should never reach Earth's surface because they simply would not live long enough. But they do reach the surface, all the time. Why? Because they move close to the speed of light. From our perspective, their internal clocks run slower. Their time is dilated, so they live long enough to travel the distance. From the muon's perspective, the Earth's atmosphere is contracted, making the distance shorter. Two descriptions. One reality. Another everyday example is GPS. The satellites that allow your phone to know your location carry extremely precise atomic clocks. Those clocks tick at a slightly different rate than clocks on Earth. Part of the difference comes from special relativity, because the satellites are moving quickly. Another part comes from general relativity, because they are in a different gravitational field. Without correcting for these relativistic effects, GPS would accumulate huge errors very quickly. So every time you use navigation on your phone, you are relying on Einstein being correct. And when you look at the night sky, remember this: the light entering your eyes may have traveled billions of years to reach you. During that time, galaxies moved, stars lived and died, and entire cosmic eras passed. But along the photon's path, the proper time is zero. That is the strange and beautiful truth revealed by relativity. The universe is not a simple stage with clocks attached to it. It is a deep geometric structure, where space, time, light, motion, and causality are woven together. And perhaps that is the most beautiful part of all. A simple question: why does time not pass for light? Leads us to discover that reality itself is far stranger, more elegant, and more profound than we ever imagined.